This is the Empower Podcast. Released July 28th, 2019. Episode 452. An interview with Kieran O'Leary. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
Hi, I'm Kieran O'Leary, and my company is Mixed Signal Systems. I'm based in Edinburgh, Scotland.
Hey, Kieran, how you doing?
Yeah, great, thanks. Good to talk to you at almost 1 a.m.
Yeah, it's real late over there. But you were a night owl, and that seems to work out well. You were filling in nicely for a cancellation we had. I really appreciate that. And I know you're from the consulting forum. So what kind of consulting do you do?
So the clue is in the name, really. So the company name is Mixed Signal Systems. So our core competency is in designing high-performance mixed signal products. So products with both analog and digital elements. So that core strength allows us to design products for a wide variety of markets and applications. So, of course, at the moment, there's a lot of work in the IoT space, with a variety of sensors and sensor fusion and so forth. But based on my background, we do a lot of work in the audio electronics space, right through to kind of high bandwidth multi-gigabit systems, such data acquisition units and so forth.
That sounds kind of tough.
Well, in some ways it is. I mean, the way my career has gone, the bandwidth has gone down, but the bit count has gone up. Does that make sense? Yes.
Yeah.
So you might have, a 12-bit video DAC or ADC, a couple hundred megahertz bandwidth, but then you move into the audio space and the bandwidth comes way down, but the bit count goes way up. So different challenges for the different markets, but the physics don't change.
Well, that's good. That's a good take on it. I mean, I like that. You're keeping a clear head on that, because it's like that's. I mean, it seems like a kind of intimidating thing to have these high bit rates or high bandwidth. What was the trade-off again? It was bit rate versus bandwidth, or So
video DAC 12-bit, but high bandwidth or higher bandwidth, and then audio, and the bandwidth comes way down, 20 kilohertz or whatever. But the bit count goes way up.
So what is your background? Like, how did you get to this point in the first place?
Well, just kind of back to the start. So, I tell from my accent, I'm Irish, but so I'm from the south of Ireland, southwest of Ireland, County Kerry, and I went to university in a fairly small university called UCC, University College Cork in Ireland. But it's got a good electronic engineering department there. But its claim to fame is George Boole, Boolean logic, was the first professor of maths there, or professor of mathematics. So did my electrical and electronic engineering degree there. And maybe we'll talk a bit about it later. But my final year project there was it was a control engineering project, and I worked on the control algorithm for a robotic arm. And my classmate, colleague of mine, it did the power electronics, and everything worked remarkably well. Everything spread out on the bench with a nice little DSP running the control algorithm, and all the power electronics controlling multiple motors for this robotic arm. And then the open day was approaching, so we said, we better make this robot look a bit nicer. So we popped everything into an enclosure, and of course it looked amazing, but on the open day, the robot took on a mind of its own and went berserk. And that's when I first learned about EMC and signal integrity. And I promised myself then, never would an EMC issue make me look like a fool again. But of course, that strictly speaking, it wasn't true. But I learned my lesson, early, and since then I've always had an interest in that side of things. But
that's great.
I was a graduate in Xilinx in Dublin. Their European headquarters was in Dublin, and it was a really interesting time to be in Xilinx, actually, because it was the early 2000s, just after the dot-com bubble burst. And at the time, it's still the case, but particularly at the time, an overwhelming majority of Xilinx and indeed Altera's revenue came from the telecommunications market. Now, there was some other areas like military and aerospace and all that. But for the most part, it was the telecommunications industry. And of course, at the time, it was a difficult time for for a lot of companies in that industry. So it was an interesting time to be at Xilinx, and worked in the embedded applications team there as a customer applications engineer. So the early days, hear Dave, talking about it often about, with the FPGAs, how there's more and more of an integration of hard IP, and to go along with the FPGA fabric. And that was really around the time, the early 2000s, when they started that. So with the PowerPC embedded in the Vertex 2 Pro.
Oh yeah.
So that was their first device, and the microblaze had just, kind of come into being, and that was, God, it's a long time ago now, but it was kind of the natural evolution for the FPGA fabric. Like, you needed more than just a big array of lookup tables. You needed a bit more, and that evolution has continued to today. But that was a couple of years there in Xilinx in Dublin, and
Well, before we
oh,
leave the
sorry,
designer side of things,
sure.
so tell me a little bit more. So you were on the application side of things. I mean, so you saw this going into all these different places. Um, I mean, people were using it as a joint, as the embedded micro in there, like you said, with the hard IP,
Yeah,
or
so I was in the embedded applications, um, at the time. I mean, it's very standard now, and it's completely normal nowadays. But at the time, it was quite novel that you would have maybe a telecoms base station, or something like that, and the FPGA, it could handle, masses of data. Like, the throughput would be very, very high, but you still needed a processor that didn't have to be particularly high bandwidth, but it needed to manage the routing of those transactions. So if you manage, you've a voice over IP network or something like that, and you've got all these packets, and they need to go to various locations, and it made sense that the data pipe needed to be very high bandwidth, but the management of that data pipe didn't need to be so high bandwidth. But nonetheless, it needed to take place in the system, somewhere in the system. And FPGAs, they're not cheap now. They certainly weren't cheap then. So perhaps it made sense to accommodate the cost of the processor, within the FPGA fabric, or within the system on chip. And there was lots of applications where that made sense. Robotics was an area where it made a lot of sense, and it was the type of application where those, really kind of top end FPGAs were able to find a good place in the market, where you had, on one hand, high bandwidth requirements, but on the other hand, you needed a management system to make sure that data was taken from the right location, and piped through to the right location. And the evolution since has kind of proved that strategy right. There's FPGAs, they're power hungry. They don't have the absolute performance perhaps that an ASIC would have, but they've got other advantages that are fantastic in a lot of applications. And we see that now, with all the various hard IP, with the multi-gigabit interfaces. Even quite recently, Xilinx brought out an RF SoC, which is quite novel, that had an RF, or multiple RF DACs and ADCs integrated into the package, onto the die, so that you can do, entire software-defined radio or radar systems on chip. You can do your DSP, all this kind of thing, and that all started back, nearly 20 years ago now, where like the FPGA was, a very high performance CPLD. We're glue logic and we're piping this from A to B, and of course, FPGAs were capable of much more, and then
yeah,
we just happened
yeah,
to
that's great.
be there at
I
the
mean,
time.
it's crazy how it's moved in the RF space as well, and how I guess the integration on a chip and like the changes in process have also allowed that as well, because higher speed, higher performance type stuff, or even more exotic stuff that RF sometimes requires, being able to put that all in the same die
Yeah,
is very, very impressive.
I think that's a fair point. I mean, there's a couple of things there to trade off, and the guys in Xilinx clearly think it's worth to trade off. You've got, an FPGA is, perhaps the noisiest thing electromagnetically that you might have in your board, outside possibly, the power supply. So putting that, right next to your RF front end, is quite an interesting strategy. But there are good reasons to do it. I mean, there's nowadays something that people don't often think of is if you lay down an interface between two devices on a PCB, that can be quite power hungry actually when you're transmitting gigabits of data, and the bandwidth the bandwidth of the channel of the interface between the two devices is quite high. There's capacitance on the track and everything. As you switch your ones and zeros, even in a serial manner, that can
Yeah,
consume
right.
quite a lot of power. And if you can localize that, maybe you can save some of that power. That can be advantageous. Of course, there's the space saving. I mean, what I think would be really cool is to take one of those RF SoCs, which have multiple RF DACs and RF ADCs, and you've got a couple of processors in there, and a big FPGA fabric, and you could do something really cool with a drone. You could build your entire drone or UAV around this one device. You could have your remote, your remote control of the RC radio, if you want to think of it that way, coming in over one antenna, and you could have passive radar to see what else is around you. You could have your motor control. All these different
Oh
things can be
yeah.
done in one chip. And of course, I mean, it might be the world's most expensive hobby drone, but it could be a really cool
You're right.
could be a really
Fifteen
cool
thousand dollar
platform.
drone.
Yeah, and the battery, like
You start weeping every time it crashes.
yeah, oh, well, yeah, that's the thing. And typically you think of the drone motors consuming the power, and you go, oh well, this is kind of funny power profile here. The processor controlling the motors is drawing as much power as the as the motors, but it's that level of integration where you could even imagine one system on chip doing the RF, doing the motor control, doing any kind of Kalman filtering or anything like that, for any kind of three-dimensional position estimation and stabilization, these kind of things all in one chip. It really is quite impressive. And the Altera guys might say different, but of course, but from a Xilinx perspective, you can trace that back to the Vertex 2 Pro, which was a Vertex 2 with a little bit of vision, perhaps.
Hmm.
And
That's great.
yeah, so
Well, so that role was it was a application engineer, and then you kind of kept doing that later on. I mean, we've had a couple applications engineers through here on the show, but like, what is that experience like? And then how did that end up playing then into consulting as well?
Okay, yeah, I'm glad you asked me that, because I've been a long time listener of of the Ampar, and I really enjoy it. And one time I remember you were having some discussion about FAEs, field applications engineers, who are typically really the front line when dealing with with customers from a technical perspective. And Dave said something like, I can do without the FEs, I know what I'm doing. And I was just screaming at the radio or whatever, like, going, oh my god, I need to stand up for the
This is a
applications
common
engineers.
a common thing, so I wouldn't.
Yeah, I understand, but there and it is. I mean, applications engineering is a broad church, and like it's not typical, perhaps, like that you would go from applications engineering into consultancy necessarily. So it is worth maybe kind of exploring that, and even talking among applications engineers, like, how would you define your role? And it's one of those roles that can be difficult to define, but basically your job is to shepherd the design from the development organization, in your company, into the customer's hands in a finished product. And and depending on the type of applications engineer that you are, it is your responsibility, kind of as a team, to ensure that from a technical perspective, that the silicon or the device comes from your organization into the customer's organization, that it works in the application, that to a standard that the customer is satisfied with. And that means there's a great deal of tasks that need to be done to ensure that that's the case. Like I said, the FEs, the field applications engineers, they're out there day in, day out, engaging with customers, working on technical solutions, for the customer's application. And for smaller clients, that aren't using, the latest technology, it can seem like that the FE is just kind of a technical resource that I can do without, if you know what you're doing, but for strategic customers of a semiconductor company, the relationship with the FE is vital, because of course they'll be dealing with engineering samples, brand new silicon, and there may not be a data sheet available. The silicon you're working with may be engineering samples. There'll be a lot of errata. You might have a very strong relationship with a particular customer, and you'll want to get feedback from that customer. They'll want their guy that they can pick up the phone and they can go, hey, look, we're just not getting to performance here. Like, my background is in mixed signal products, and maybe the digital side is fine, but maybe the performance of the ADC just isn't up to scratch. Now, part of that can be, with a sophisticated ADC or DAC, there can be, quite a lot to configure them to get the performance that you expect. Or it might be that the silicon just isn't up to it, and that needs to be managed. And of course, sometimes you think that a semiconductor sells silicon. Of course, it doesn't. It sells a solution to a customer's problem, and
Right.
along with the silicon,
that sounds like a consultant or someone who's selling
yeah,
selling their services, pretty much.
yeah, but it is very important, because it is one of those things, like, I've just for many years, discussions with other groups within the organization, and it's, they'd say, like, oh, well, we don't really know what you applications engineers do, and you say, well, you'll know it when we're not here. And it really is a case, like, of the next time your ADC or DAC or whatever doesn't quite work, when the customer rings you directly, and he interrupts your workflow, and he says, well, we don't care, like that, you're working on the next revision of silicon, like, you need to get this silicon working, and you need to help us understand how to integrate that into our platform and get the analog performance that we need. And there's a lot of effort goes into that, writing data sheets, errata, all the way through to the more strategic stuff of, like, managing the relationship, and even, next generation definition of next generation silicon, or even to some degree involvement in pricing discussions. Of course, you're not a sales engineer or technical marketing guy, but you have to try to understand what the market will bear at a particular price point and so forth, and that does require technical knowledge.
Yeah, I think the thing that would be scariest for me would be, so many times me as a consulting engineer or working as an electrical engineer at a company, there's always someone to ask a question to. There's always someone, like, I can be like, assuming I get enough attention from a vendor, I can go and ask, a local distributor rep or FAE distributor, or moving on up to the actual FAE at that company, or, and then sometimes they say, hey, let me call the factory, the AEs, I can talk to them or whatever. And, there's always someone up the chain I can talk to. But I imagine that in application engineering, like, you can go talk to the silicon designer, but sometimes you're just like, I'm the end. I am the person that figures this out. So yeah. I'm sure that you've run into that a couple times.
Yeah, I mean, of course, if the organization is working well, you never feel on your own. But sometimes, I mean, it's just a business reality, and I guess perhaps that's a thing that maybe applications engineers sometimes, particularly more junior applications engineers relative to junior design engineers, will have much more of an appreciation of the business case, or the business environment. Now, as designers become more senior, they're exposed to more of that within the organization, but typically an applications engineer will get that much earlier in their career, at a more junior level, and you might be the end of the line in the sense that the business case just simply isn't here, to involve the designers, maybe to do new silicon revision, or to do the level of research required, to come up with a solution. It just may not be economically viable, and sometimes that can be a difficult discussion with a customer, but sometimes in conjunction with your sales guys, that is left to the applications engineer. That's what you're trying to do. You're trying to get the right product for the application. And actually, in many ways, that was a good grounding. Moving later on into a consultancy role. Actually, there was some benefits to that. The understanding that communication is important, trust with a customer. If you have a good ongoing relationship with your customer, and one time, it's not that you're letting them down, it's just, unfortunately, at this time we can't deliver that particular requirement, but please understand, for the long term, we intend to have a relationship with you, and it will be in the next silicon, or it will be in the next product, or we will do our best for you, and all those experiences built up over the years as an applications engineer on site with customers, or dealing with them remotely, does give a perspective that perhaps would be helpful for somebody, interested in being a consultant themselves.
I guess that I'm interested in that relationship you're talking about too, because you're talking about like the key customers. So these are like large scale, big businesses that are going to buy millions of units. What was that actually like? Was that akin to like an FAE, or was it more like a hand holding type of thing because it was so early days on early silicon, or what?
So in my in you know in, before I went out my own, I was in three companies, three semiconductor companies. So I was with Xilinx and later Analog Devices and Wolfson Microelectronics, and in each of those companies, we were dealing with strategic customers or tier one customers. Like there's different terms for them, but people appreciate where the majority of the money is coming from, and of course they, like any other business, they get the premium support. So those large customers, they will have FEs in any reasonably sized semiconductor company. The very large customers will have dedicated FEs, particular even within an organization, say like Apple or Samsung or somebody like Panasonic, the really big companies, particular subgroups within those organizations will have FEs assigned to them. And those guys are there on site every day. Behind the FE, then there's a team of remote AEs, back at the factory, as it were. But for the large strategic customers, if the phone rings and the FE says, or the sales guy locally says, "Look, we need an AE." And he needs to get on a plane. It's not uncommon at all, for an applications engineer to hear on a Friday that, okay, you need to be in Seoul or Tokyo or California, in San Francisco, or in perhaps Seattle on Monday morning, and away you go.
Oh wow,
yeah.
yeah.
But it's just the nature of the business, and part of it is.
I mean, you do have 2 days to get there, so that's nice, right? I
Yeah,
mean, like,
yeah.
it's not like you have to be here right away,
Yeah,
you know?
you do hear some stories like, yeah, it happened to me quite often, like depending on the time zones, you want to make the most of your weekend at home. So you would fly at a time where you'd fly into, perhaps somewhere in the Far East, and you go straight from the airport to the client. And that,
Oh yeah,
and then that's just one of the aspects of being an AE. But it can be hugely rewarding. It can be great because if you work with these strategic clients, you have, you get to work on the leading technology, so if you're doing the best, in my case in the past, maybe it was a video DAC or video ADC or audio DAC or audio system on chip or something like that, and then you find them that they're in, like you can imagine, the big phone companies, Apple,
yeah.
Samsung,
Consumer
okay,
level,
yeah,
something, yeah,
and then you're there,
right,
like,
right.
oh wow, when that phone comes out and everybody's just going, oh, that's awesome, and then you're going, yeah, it's amazing. I was involved in the design of that, or the system integration of that, and you really see how many people these big companies take to bring a product to market, and
Right.
again, in a consultancy role where you're wondering, okay, well, how can I contribute, or where you're responsible for hand holding a client all the way through to production, if you're dealing with these companies and they're pushing through 1 million of your units a week, it's a statistical certainty that any problem in your design is going to surface. So if you have, if your process isn't in control and you're dealing with silicon, and you've got some kind of parameter, and it's not down the center, your normal distribution just isn't quite tight enough. If you're shipping tens or hundreds of units, you're not going to have a problem with temperature or voltage. You'll get away with it. But when you're shipping 1 million units a week, you gain an appreciation of things like Six Sigma and quality, and what
Yep.
what the quality engineers are doing and why they're important, and make sure to be nice to them, because they or even
Right,
some
right.
product engineers, process engineers, all these guys that you don't typically see it, the value that they add in, or in smaller production runs. But once you're shipping large enough volumes, and that goes for startups or SMEs that plan to scale, you might get away with a lot simply because you can just manage it if something goes wrong. You've you ship 100 units and you've a 1% failure rate. If you yield a 99%, you've got one device coming back, and it's inconvenient to ship the guy another one. If you're shipping 1 million units and you've got 1% of them coming back, you have a big problem. And from an applications engineering perspective, yeah, somebody will pick up the phone and you'll hear about it, and you may be on the next flight, you may be on the next plane, and that's just part of the role. But some guys really like it because you get to see the world, and you get to experience different cultures and everything, But
Sure, sure, sure.
so
So that's interesting too about the it always calls back into sharp relief. Like, I'm just a person. I always complain about like, oh, look, I can't get this out of distribution, and that's as a small person, that's all I really. That's my immediate. That's like 1 meter in front of my nose kind of problem. Like it's just what I have to deal with on a daily basis. But then like really thinking about it, like thinking about like what you were saying about how many people are involved in just a single piece of silicon, it really is mind boggling. Obviously, and the fact that it's most of the time, it was not even close to develop for someone like me. I'm just benefiting from it. I'm benefiting from the Samsungs and the Apples of the world, and the fact that there's, sensors out there that I can maybe use, or op amps that were, that Northrop Grumman needed for something, and they, oh yeah, well, we'll just sell these to the public too.
yeah, sometimes it can be frustrating. And I experience it myself now, being on the other side, dealing with much smaller clients. But sometimes you don't want the cutting edge silicon, like for any number of reasons. But if you think about these things from a business perspective, if something goes wrong with new silicon, and there's a workaround to be had or an issue to be investigated, the strategic customers are going to get that support. They're going to have an applications engineer on the plane. They're going to have the local FE working the long hours. They're going to have their sales engineer or account manager, speaking up for them within the semiconductor company's organization. But if you get that cutting edge silicon, who's going to speak up for you? If something goes wrong. So when I was in Xilinx, actually, as a graduate, somebody said one time, and it's always stuck with me, that you want to be on the leading edge, but you don't want to be on the bleeding edge. And because if you're a small and the Xilinx felt that they had that problem themselves, at the time they were quite frustrated because FPGAs kind of always push the process nodes.
Sure,
and
sure,
they always
7 nanometers, right?
Yeah,
Screw that.
and I'm sure guys in Intel or AMD or whatever will tell you the same. They feel like that they're doing all the research, or IBM or whoever, they're doing all the research, and other companies are benefiting from it.
Yep,
So if you're an organization that can manage those relationships and absorb the cost if something goes wrong, you deserve the benefit of being on right at the edge. But if you're a small organization, maybe bear in mind that can I do what I need to achieve from a product perspective without getting the latest whiz bang thing? And sometimes you can't. Sometimes your product is a hardware product that needs absolutely the cutting edge stuff, but sometimes you don't. And I can completely understand that it's frustrating for smaller customers, but it is a business, and the guys with the most money, they're going to get first dibs on support and access to silicon and everything. And sometimes it's good, even picking your suppliers. There's some companies that I typically won't design in almost at any price. So you kind of know what I'm talking about.
I don't know of any of these that right.
You can guess.
Here's the thing I always think about them, and if people have listened, exactly, people have listening, they've heard the show before, they know who we're probably talking about. The ones who get that tier 1 support probably friggin' love them, though.
I'd imagine so. Yeah.
It's just like how they're set up. Their setup's so different, and it's fine, but it's just, there's some companies, like you're saying, do not support the smaller mid-sized enterprises.
And I think that's perfectly fine. I think the problem comes, and I've worked in companies, we've had this discussion. You set out your stall, you set up the business a particular way, and if your business is targeting tier 1 companies in automotive or tier 1 companies in consumer, and you pursue that market, and then you just tell, even tier 2 companies, let alone tier 10, if you like, we're not interested in your business. We don't think you're bad guys, but it just doesn't suit our business model.
Yeah,
that's
right.
Fine. And then you get other guys like TI who'll support everybody, and they've got their application structure and their sales structure and everything set up to do that, to support everybody as best they can. That's fine. The problem is the companies that kind of maybe get a bit greedy. Well, let's manage the relationship with the tier 1s, and then let's just sell to the tier twos, tier
Right,
three.
we'll just sell the offcuts,
Yeah,
you know,
and
like
then and
yeah.
going,
You
well,
can have the soup bones and
yeah, and
the
it,
tripe of our.
yeah, and for you do wonder for the amount of money that they make out of it, revenue wise, is it worth the reputational damage, or people going, oh, they're just difficult to work with, or
Well,
they
I don't think the amp
yeah.
hour. I don't think the amp hour is going to be any kind of dent, unfortunately. So,
Yeah, like so, yeah, it's interesting, and like I say, applications engineers, particularly have to keep their ears open, because they're hanging around with the sales guys and that sometimes, maybe
yeah.
get exposed to these kind of discussions earlier in their career than a design engineer would, back in the factory, because when you start out as a graduate all the way maybe up to senior design engineer, you're expected to make absolutely the best performing circuit design that you can, and that takes a lot of time. That's a full-time job in itself, and as you become more senior in the design organization, that's where the discussions on price and perhaps other things come in.
So, what about were you making like dev boards then for customers, like ones that would be like broadly distributed,
Oh yeah,
like
yeah.
ones that like we would buy off the shelf? Because I'm always curious about that process, like internally on chip companies.
um Again, it depends on on how your company is set up, but a lot of the evaluation boards, development kits, reference designs, and so forth that I worked on would never be seen on DigiKey or Mouser or Farnell, because if the silicon isn't made for the general market or mass market, then there's no point in releasing the development kit to the mass market. But yeah, some of the boards I worked on would be available on these distributor websites to support the silicon, but of course at a horrendous markup. And as some of that is the price of the components, but some of it is typically a strategic decision that perhaps you might see a board for $500 or $1,000. But of course, you say, well, you'll know like that it doesn't cost $1,000. It might cost $100, $200, and they're not trying to make money out of the boards. They're trying to discourage, what you might call the tire kickers. Like where somebody wants to do a hobby project. And my background in audio electronics, you see this a lot, that you get guys that are really enthusiastic about audio, and then they get really frustrated. Oh, why do I have to pay a couple of $100 for an audio DAC reference board? It's a very simple board. It's just got some pen header, interface to the DAC and some jumpers to control the settings. Why is it so expensive? And the reason is, kind of frankly speaking, that the semiconductor companies are in business, and if there's any issues encountered with the with the guys buying these boards, perhaps they'll never recover the cost of even supporting the customer.
What would be the interactions at the beginning? Is it just like, well, let's just come up with something interesting? Is it an eval board that is just like, well, let's just break out the pins and make it do a thing? Or is it like, let's make this do an interesting thing in the case of like more commercially available dev kits?
It really depends on what you're targeting. It's not uncommon to see and to see three or four different types of boards, and I mean, I've no commercial relationship with Nordic Semiconductor, for example, but they're a company that seems to do this well. You might see like, okay, you've got a very small, relatively speaking, form factor board that will show one of their Bluetooth devices, on the size of a coin cell or something like that, and then they'll have a larger board which you might consider a reference design or something like that. Which is a lot more broken out, but allows you to to do a little bit more. And then they'll have a full scale development kit that will allow you to do current measurements and things like that. And I think they're a good example of a company that does it well for the mass market. And like I say, I've got no relationship with them other than I think that they handle that kind of side of things well, and they are clearly targeting mass market with the IoT. And that somebody has sat down there and said, well, we need a form factor thing. We need something that people, the firmware engineers can get their hands on, and then we need something that things like current measurements are actually quite important. Like for pretty much for all products nowadays, but certainly for anything battery powered, and you do need a different board. You do need a different board for for these different tasks. Of course, internally then, which the customer will never see unless perhaps you're a tier 1 customer and you're given one out of courtesy. There will be a whole other range of boards supporting the device as well. So you'll have design evaluation boards, which may be a much grander version of the board that a customer might use for for current measurement. The design evaluation or the design verification engineers may have a much more sophisticated version of that board that can be used for lots of performance related measurements. Like my background in the audio space. For taking measurements like SNR and THD, current measurements, of course. These kind of things. The board performance needs to be very, very high, because you don't want to be measuring the performance of the board. You want to be measuring the performance of the silicon. And then sometimes, if you want very, very high performance, on an analog power supply, you might need to, spend a little bit more money or take a little bit more area in the power supply section of the board, which of course you don't want to pass along to the customer if they just want to evaluate the part with all the supplies ganged up. So, and of course, then there's internal test boards, which can be, quite complex boards. Then, it's endless depending on the type of silicon that you have, or the device complexity.
Got it. Yeah. So what would you usually end up getting? I mean, would you start with something that was like bonded silicon that's like basically just an eval like coming out of the fab, or like what was that? So like let's walk through maybe something's a new product's rolling off the line. Can you walk us through what the process would be like?
From a design evaluation or applications engineering perspective?
All the way. So yeah. So all the way. So we're gonna say the new chip. Awesome DAC 45, right? Awesome DAC 45, awesome DAC 450. That's even better. Better than 45 is awesome DAC 450. So you have been talking to the silicon designers and the production folks, and you're like, all right, we're getting ready to go. What happened with like what were the boards that you would make, and then how would you then interface with the customer? In order to work with those, like how would they get those boards and work with them?
Okay, so give you the nice fairy tale or the reality. So
I mean, let's have a fairy tale with some cautionary, big bad wolves in there.
Okay, well, I mean, I can give you okay, I guess the big bad wolf is that the silicon comes back and that there's a fatal flaw, and that the thing won't boot, or it's even happened.
Sure.
It's shorting out or something like that, and then
it's a crib death for silicon.
Yeah, and that does happen. There's some kind of really funny stories that you could tell about that, but I won't embarrass anybody. But so assuming that the silicon comes back and it's in decent shape, it's an engineering sample, then if you're dealing, like with say in the consumer electronics field, timelines are very, very compressed. I mean, and you can imagine you want a new phone every year or something like that. Timelines are compressed, so it literally can be that after the silicon is comes out of the fab, it gets assembled, it just puts in a package, see if the silicon die gets diced up, off the wafer, gets put in a package and assembled. No time for testing, and it can literally happen where somebody will hand carry in an aircraft, the first, just get a commercial flight, from Asia back to the headquarters, and you'll hear people talking about, I'm hand carrying the silicon. And because they don't have time to wait, for shipping. So, and come in, and not always, of course, but if you have a high customer demand, waiting on new engineering samples. So, ideally, what will happen, of course, is you come back with the silicon. Maybe you have a couple of hundred, couple of thousand devices on a reel. And there's boards waiting for you. Now, typically, you won't. It does again depend on the device, but quite often you will have, like I said, an evaluation board, but you may have a socketed version of the evaluation board, where you'll do two versions of the evaluation board. For absolute performance, you'll take your silicon or your package and you'll pop it down, and you'll reflow or rework the board to take the silicon. The board is already done. All that's left to be put on is the device, and you'll have a technician do that for you.
Okay, wait, before we go further then, so when did you get the spec internally that allowed you to make that board?
Pretty much. I mean, if you have a good applications engineering and design evaluation team, you will know before silicon goes to the fab. Your applications engineers. And even your PCB layout engineers, if you have those internally, they will be working, with the silicon designers to know what the ball out or the pin out is before the silicon even goes to the fab. And the reason that's important, and I've been involved in projects personally where you have a CSP or a BGA, and the designers do the IC layout, or you've got a just like with a PCB, you've got PCB layout. For an IC, you have IC layout, and there's guys that specialize in that, and they lay out everything. They think it's fantastic, and then it comes up with a pinout, which the PCB layout guy looks at and goes, "Oh, I simply cannot route that out." So back to the drawing board, and then and it does happen. It literally made the cost.
Oh, I was amazed. I was amazed when a early. I had some access to some early stuff, and they said, look, this is not a finalized pinout yet, and I'm just like, what? What do you mean it's not finalized yet? They're like, yeah, it just might move.
Yeah.
What are you talking about? Okay, I guess I won't design anything to your pinout then.
Yeah.
But geez,
it does happen, certainly. And again, depending how quickly things are moving, the silicon might go, you mightn't even have the pinout finalized. And okay, well, when we're we're bonding it out, that'll come later. And that does happen with very compressed timelines in certain industries. Of course, you want to avoid it if you can, for quality and to reduce the risks of making mistakes. But sometimes you can't help it. So you want your PCB layout guys involved, you want your applications engineers guys involved, and as soon as the silicon goes, probably even before it, your guys will be doing the schematic capture for that PCB, and then just like any other PCB, you'll review it. Hopefully, do your schematic review, do your layout review, and then your PCB. Typically, of course, your PCB will come back quicker than the silicon, because it just takes longer for silicon to be.
For now, man. I'm just seeing a future
the chip
where
printer.
Yeah, right. You've been listening too long.
Yeah. So I can't wait till the chip printer comes.
Yeah, right.
So.
Right.
So that all happens. It comes back, and like I say, you might have a socketed version where like these chips are coming back, and they won't have been tested. You won't have time to test them quite often, or you won't have a test program in place, an IC test program in place, because the test engineer won't have time to. They need physical samples to test their test program before they can deploy it. To the assembly site, perhaps where it will be tested. So quite often people will design a custom socket, and they can be quite expensive. I mean, those sockets can run to thousands of dollars,
I believe it. I mean, especially if it's like BGA or something, it's got to be super perfectly aligned and have like connections out to everything.
And you don't want to lose performance. Now, like I worked a lot, in the audio space, and where you might have a THD measurement, so total harmonic distortion. So without knowing too much about audio, you can imagine distortion is bad. And if you're giving up some performance on the connection between the socket and the device, your THD measurements can look quite poor, because you don't have a good electrical connection between the socket and the device. And if you're pushing the boundaries of a given technology, or for any number of reasons, your performance may not look fantastic in the socket. So you might take, get somebody to test 10, 20, 50 of these boards in the socket, for functional, functional certainty, or certainty that they're functionally operating, or at least, some way reasonably functional. And then you would take some of those devices and have a technician put them down to the evaluation version of the board, that's done, to have the silicon, placed on the PCB, and that generally happens. And if you have time, you will do it at your home base, back at the factory, and you'll take as long as you want. You'll evaluate all the parameters and so forth, and then when you're ready, your FAE, perhaps a local guy, an applications engineer or a marketing guy, and a sales guy will all go happy out into the customer and show off your, DAC 450 or whatever you said. But it does happen where those timelines can be extremely compressed, where you will have silicon will come in untested on Thursday or Friday, and you'll test them in a socket. You'll get the 10 best golden devices. You'll pop them down on some evaluation boards, or demo boards for the client, and then on Sunday night you're on a boat, on a plane to the west coast of the US, or somewhere in Asia or something like that, so that early the next week you can bring in and hand over 5 or 10 demo boards with working silicon to a client. Now, you want to avoid that if you can, obviously, because the more time you have, the better. But the world doesn't work like that, and sometimes you just need to have compressed timelines. It's even happened on a couple of occasions when I was in Seoul, in South Korea, and I was sent to Korea to get everything ready before the silicon was available. And the silicon followed me to Korea, and I had the evaluation boards waiting with me in Korea. And we got a local a local company to rework the boards and put the silicon onto the evaluation boards so that we could bring them down to a large Korean client, which maybe you work out who they are, but like sometimes sometimes when you're working consumer electronics, it can be that compressed, and if your competitors are doing it, like you have to do it too, even if even if you do wonder sometimes, is it really this critical? You talk to the engineer and the client, then a week later, oh yeah, thanks for that, it's sitting on my desk. It happens.
So I'd love to move on to the consulting stuff in a second here, but how is that different then? So that's an evaluation board. How would that then change if you were going to be sending out a board to the general public? Is that more like future revisions of silicon?
Perhaps, but it might be that the expectation for a board for the general public would have higher requirements in terms of the supporting collateral. So you might want to have, make sure that you've got a really good, clean schematic that you'd be happy to show to a client, or a customer. You might want to even make the Gerbers available. Quite often, for a silicon company, they'll make everything available. They'll make the Gerbers available. I mean, it doesn't cost them anything if you copy the board, but they might want to, make it easy to see what the layout under a BGA or CSP or something is like. And then, of course, they'll give it to you in a PDF. They might even give you the original files, Altium, Eagle, whatever it is, all this kind of stuff.
Yeah, how about KiCad? Come on, man.
KiCad, yeah. Well, again, it does depend. A lot of the silicon companies, they've got actually vendor relationships with, with maybe companies like Mentor Graphics or Cadence or something, and they might do they'll do an overall, package by for their various tools. So it might be some time before you see KiCad. But again, if you're targeting the mass market, I'd imagine, for example, IoT, it would make a lot of sense to support things like Eagle and KiCad and so forth, because there's a lot of perfectly profitable companies that'll buy plenty of your chips that maybe don't need Altium, or they don't need DX Designer or something, or pads or something from Mentor Graphics, and would be they'll be able to give you money. And if you can help them
exactly,
out,
right? Yeah. Money still talks, even if it's using open source software in order to help promote the product.
Absolutely,
right?
And it does come back to what your business model is. If you're targeting tier ones and the tier one uses Altium, give them the Altium files. If you're
if
you're doing
service business,
if you're doing horizontal, then you have to look at what the market is doing, and some of the companies that you would consider good at supporting a broad base of the industry, they can be. They can be quite supportive of platforms like KiCad, but of course, again, they are a business, and they need to they need to manage the time that they put into creating.
Sure. I know mine was mostly just a general gripe, not an actual thing. Like I don't expect it.
But it's fair. But it's fair. I think some companies need to do it, other companies don't. Depending on what they're targeting, or maybe should do it rather than need to do it.
So on the consulting side, so then you transitioned into consulting. So what does that look like? I mean, does that look similar to you said that some of the stuff had prepared you for the consulting side of things, but what does that look like on a daily basis now?
So I was, I think it was 2012. I went out my own. I left Wolfson Microelectronics, and I started doing, my own consultancy work in, Mixed Signal Systems Limited. And, there's lots of reasons for becoming a consultant. So a kind of I guess a lot of guys down through the years have done things to impress a girl. A lot of the reason I became a consultant was for that reason. Like, so my now wife worked in Wolfson Microelectronics as well, and I'd always said, I'd like to. I want to go out my own. I want to do my own thing. I'd like to be my own boss, this kind of thing. And she called me on it and said, well, you keep talking about it, just do it. So so that day happened to be the day for my it happened to be the day for my performance review. So I went in to my manager, a good guy, and he was getting all the paperwork ready for your performance review or whatever. I said, I'll save you the paperwork. I'm off, He's like, what? So yeah, I'm going to go out
Oh
on my own.
man.
Yeah. And
Wow.
yeah, so one of it, I kind of being a bit flippant, but but yeah, she did really call me on it and said, well, like, what are you waiting for? If you're going to do it, do it. And yeah, I'm glad she did, because it's worked out. But the other reason is I was traveling really, really, really a lot as an applications engineer, and maybe I
Yeah.
didn't want to travel so much.
Right. You just say you were in Korea quite a bit, and that'll take the
Yeah,
toll on the
yeah,
body.
like yeah. I mean, if anybody has worked with the Koreans, I mean, they really know how to work hard. Like I really
They
enjoyed my
party hard.
time.
Don't forget that. Don't
Yeah,
forget
that's the thing.
the
Yeah,
soju
yeah. The Irish of
ganbai.
the Orient. Yeah,
Yeah.
they
That's great.
yeah. I really enjoyed my time there. Really liked it. But I was never based full time in Korea. But at the end of my time in Wolfson, I was there for
Yeah.
5 years. I totted up my time. I was five
Yeah.
years in Wolfson, and I was a year and a half all in Korea, and I was never
Oh
based in
my
Korea.
goodness.
I was about
Wow.
25% of my time, and that was tough. After a
Yeah.
while, like so. Yeah, anybody who gets the chance to go to Korea, you should go there. It's a wonderful place, and
Oh man, so
yeah,
I used to work for Samsung, and I
yeah,
like my coworkers were amazing, but like such a hardworking top down like militaristic style
yeah,
management, and it's just like, oh,
yeah,
I did not do well there, and like
yeah,
that's almost like the opposite of what consulting is, which is kind of interesting. It's like instead of like being told exactly what to do by your superior, who was told by their superior, told by their superior, now you're like, oh, I guess I'll
yeah,
just work for
yeah.
this one person.
It is, yeah, it is quite a change, but I don't regret doing it. And nowadays, I have two types of clients. Really, I have SMEs and startups that will hire me to do product development work. In the mixed signal space. So, they have an IoT product that they have in mind. So, a lot of sensors, so maybe a lot of analog design, some RF design, firmware development, typical product development that you might expect from an EE. Sorry, excuse me, working as a consultant. I don't typically have medium-sized enterprises as clients, typically, because if they wanted a hardware engineer, a firmware engineer, an RF guy, they would hire those people.
Hmm.
But and I think a lot of consultants would kind of say the same. But then with my background in semiconductors, I do some consultancy work for the large semiconductor companies, whether that is how to engage with clients, so perhaps how to engage with clients from the Far East, from Korea or China, that kind of thing, because, there is cultural differences and so forth. And like you say, with Samsung, yeah, there is an expectation of how work is to be done. So some of that type of consultancy. And then, of course, technical consultancy as well. So maybe there's a particular block of work they want to outsource, like write a data sheet or design an eval board, or a reference design, or even help with some aspects of IC design. I don't typically do analog IC design. I do perhaps some digital IC design, because from my background in FPGAs, it's largely similar. But there may be problems with performance of a particular IC, and there might need to be design evaluation or design debug, around the signal integrity space, or analog performance space, where there might be noise coupling or this kind of thing. And that's the kind of work that perhaps would suit a consultant for a large company. You don't need somebody full time for that, but the issue nonetheless does need to be resolved, and they either need a bit of help because they've kind of struck out trying to do it themselves, or they simply don't have the bandwidth. It's quite common, and
Yeah.
they just need some extra help. So
Yeah, does that mean you get pulled in? You get pulled in like as a almost like a contractor more than a consultant? Then I mean, in that case, because that sounds like I just wonder about the integration with a large scale company like that,
um,
because you're basically you're acting kind of on behalf of them instead of just like being like delivering. Hey, I'm going to make you a board. It's now like, hey, I'm going to. I guess writing a data sheet, you could deliver the data sheet, but some of that stuff sounded like it was more of a being embedded in the company
yeah,
more.
yeah. Sometimes, yeah. Like, I mean, there is. And sometimes it's nice for me, so I have a home office, and you'd hear other consultants say as well, it can get quite lonely if you're doing that all the time. And sometimes it's nice to be on site, with other people, and quite often you have to be, if you're debugging silicon or something, like, I have
Sure, yeah.
quite a good setup at
I'm just
home.
gonna take this home.
Yeah.
We're cool. We're cool.
Yeah, and I'm just going to bring your spectrum analyzer with me, and like if you work in the audio space, like typically you have an AP APE, like an
Sure.
audio precision analyzer, and you go, yeah, I'll just take it on the
Yeah.
bus, it's fine. Of course that's not going to
Yeah.
happen. Yeah, sometimes you need to be on site if you're doing a debug or something like that. But of course, writing a data sheet you can do from anywhere, or if you're doing a reference design, quite often they're happy for you to like a lot of the work with a reference design or something is a block of work that can be all encompassing and can be just given to somebody to do. And sometimes they want it done on site, and sometimes they don't.
Yeah. It's like a mini product almost. It's
Yeah,
like
yeah, it
the
is.
output is basically a board and the
Yeah,
stuff surrounding it.
and yeah, there is. And with a background in doing this, there is a little bit of a difference designing an application, a design, a reference design or an evaluation board, because it is a deliverable that a client will see. And if the you know yourself, like, but quite often maybe schematics, like there might be a spelling mistake in the schematic, and in some sense, who cares? But in another sense, this is a deliverable that a client, they're going to see. And if you're making spelling mistakes or
Right.
calculation mistakes and notes on a schematic, well, I can't see what's inside your IC, but I know that you didn't take the care to do the schematic well. So
Right. Right.
and so there is
Right. It's like a best foot forward kind of thing,
yeah,
right?
it is like the Alicia from embedded the embedded podcast. She speaks a lot on Jack Gansel and some other guys about the concept of technical debt. And there is a thing like you get the small little mistake there on the schematic, but that stays with you all the way through. Every client that has that, like I remember one, I'll never forget it. We had a stabilization capacitor, for an internal LDO on an IC, and in early version of the schematic, it was, or the datasheet, it was down as 1 microfarad, and it needed to be 4.7 microfarads, and every project
Oh.
in the large client did it at 1 microfarad, and most of them the FEs caught, or me and my colleagues caught, but one or two got through. And then when they were doing their early production ones, and when these large clients do an early production
Yep.
one, there could be 10,000 units, and it's like, oh yeah, it's just noisy as heck, and what's going on? And then you look at the schematic and so like, even though again with small clients, maybe you don't see this thing in early production, it could be 10 parts, but when you've 1,000 or 10,000 parts, there is an expectation
right.
that you get this right, and quality is important. So sometimes working with these companies, if they don't have the resource available internally, it's nice to be able to give it to somebody who has an appreciation of what can go wrong if you don't pay attention to even small design notes in a schematic or in a datasheet.
Well, you had mentioned when we were talking before the show too. I mean, you talk about doing signal integrity stuff, and that's kind of part of the mixed signal system side of things. What are some of the common mistakes you see either clients, not even clients doing, but what are some of the things that you feel tripped up by, or you think listeners might be tripped up by in the mixed signal space that they should be watching out for?
Okay, there's one and one only, and it's I actually have it written on my schematics, on all my schematics that I do. It's down as a note at the bottom of as part of the frame, and it just says current flows and loops always. Either you or James Clerk Maxwell is going to choose the return path, and that's it. If you remember that, whether you're doing
That's great.
digital,
Yeah.
RF, analog, it doesn't matter. If you remember that there is a return current, and you just think about, like, I don't care how complex your design is, just remember the light bulb. Once you flick that switch on the light bulb, current is coming back. And it is something, and Howard Johnson speaks about this in that high-speed digital design guy, the author of that book. He mentioned that, but
Past guest
perhaps
of the show before you
yes,
retired.
absolutely. Yeah, absolutely. Great episode. My favorite episode, actually. And he's a good guy. Actually, he's a great guy. But he speaks to the fact that maybe particularly digital designers, you put a ground symbol on your schematic, and that's it. Like, you're done. And that probably accounts for and that accounts for a lot, because that ground symbol is where where good signals go when they die. And of course, of course,
It's like a bucket, and then
yeah.
eventually there's someone that kind of carries that bucket back to the source, and then it's fine.
Yeah, it's and that really is key. If you a lack of appreciation of the return current, I would suggest, is the root cause of well, maybe it's not the root cause, because of course there's physical root causes, but it's a certainly a strong contributory factor to to the majority of signal integrity and quite often EMC issues, because you hear people talk about things. Oh, I need a split ground plane, which like one of those religious wars. Whether you do or you don't. But a lot of it comes down to, well, I need the split ground plane, and essentially what you're trying to do is manage the return currents. But if you understand why there's a return current, the properties of the return current, then you can, for very, very high performance DACs and ADCs, or PLLs is another one, phase lock loops, are ones that can be quite sensitive to noise on the ground plane or even the power plane. An appreciation of why you have a return current. Remember the light bulb, and how that return current is going to behave on a power plane or on a ground plane. That is more effort in understanding what's going on there would solve really a lot of problems. There are secondary issues as well, but by an overwhelming majority, I would suggest that that's something, if people understood, they would they'd probably make a lot of progress in terms of their designs. A simple DAC or ADC all the way up to the most complex systems like
Okay.
the RF SoC from Xilinx that we spoke about earlier.
So let's talk about the DAC 450. DAC 450 just came out. It's a great new product here. Really good development board, I heard. Was that what we were calling it? DAC 450?
DAC 450, yeah.
New DAC 450. Yeah.
I got rebranded anyway from the marketing guys, yeah.
Exactly, of course. It didn't test well in the
45 didn't work well, so 450 sounds better.
Right. 450 really brings more power and more of it's a bigger number, as some say.
Yeah.
Anyways, so DAC 450, you just designed a new design. It's failing emissions testing, I guess. Is that kind of the things that you would normally see? Like, what are some of the problems you would see, and then how would you diagnose it back to the point where you said, hey, current's flowing in loops and I just found this, and pointing at this on your schematic or your layout?
Okay, well, it is, and there's two ways of looking at this. Or two groups of people might look at this. So the design engineer who designed the product, and he brings it, for pre-compliance testing, or, if they have a chamber in house, or, he goes to the external house to, lab to have it tested, and he gets a report back. And of course, the design engineer knows his product quite well. If you're an applications engineer, of course, supporting the DAC 450, you perhaps have more limited information, or certainly at the beginning you've less exposure to the device, to the product and the layout and so forth. But first thing, you like always, look at the schematic. Like particularly if you're responsible for that device, you look at the schematic and make sure that the implementation is correct, because you will see things like, how that problem I described earlier as it happens came up. It was a stabilization load capacitor for the LDO, and it was spewing out all kinds of noise. Because it was oscillating. That you will see that if you're doing emissions testing, a near field probe, or you would say emissions testing. Of course, it sounds very formal and everything, but you'll get energy radiated, electromagnetic energy radiated, in the near field, and you might recognize it as an electric field or magnetic field coming off the board. And quite often, start at the schematic, make sure that the basics are right. And it sounds silly, so why would you do that? But quite often you'll capture quite a lot, or you'll get a feel for the design if perhaps the power supply looks kind of a bit
right. Does it look exactly like the reference circuit, or is it
it's amazing awry? God, the kind of variety of things that you can see. Like, for something, even for a simple device, you think, there's a phrase that I heard one actually from a guy in Analog Devices when I was there, and said, like, there's nothing foolproof to a sufficiently talented fool. And it's really amazing what people can do. But to be fair to people, some of these devices are quite complex, and you have to give them credit, that maybe it just takes a bit of hand holding. So that's the first step. Looking at the power supplies are always important. Quite often you'll get a lot of noise either conducted or radiated, from the power supplies. But assuming that everybody is done, at the schematic level, that everything's in kind of reasonable order, you will start to look perhaps at the layout, But before you do that, you might take a near field probe, because I'm thinking of, well, what do most people have available to them? And, not everybody has a big, like a big chamber that they can just do RF testing in. Like, you might want to just, take your scope probe. I think, and maybe Dave Jones might have even done a video with this, and short out the ground probe, and short out the ground, the ground and the probe tip, and you can make a little H field probe, and you can run it over your board, and you'll quite often see around the clock or something. Say perhaps you have an audio DAC or something, you might have a clock there at 12.288 megahertz. And you might see that, or multiples of that, turning up somewhere on the board. Now, if you see it over the audio DAC, then maybe that's okay, because the clock is going into the DAC. And if you see it near a crystal or an oscillator, that would be fine too, perhaps, of course, depending on the level. But one of the things that really causes a problem is, again, current flows in loops, like we said, think of the return current. And if the signal trace passes over a split, so for example, you've got a 4-layer board, your signal, the clock signal's on layer 4, and on layer 3 you've the different power planes, 3.3 volts, 1.8 volts, and so forth. If your clock signal passes over a split, on layer 3, which you have to, because 3.3 volts and 1.8 volts can't be shorted, you will cause quite an effective antenna. I mean, and it's quite remarkable, the amount of energy that even one digital signal traveling over a split on an adjacent layer can cause. And that's one of the first things I would always look for, as an applications engineer. If okay, well, your schematic looks fine, when we've looked around on the board and we say, okay, God, there's just energy oozing out of this section of the board here, and it doesn't really seem to make a lot of sense. Let's look at your layout. And if as soon as you see signals crossing splits, then you're going, oof, here's a real problem. And in a more general sense, perhaps, if there was one tip I could give to startup companies doing hardware products, it would be to consider this kind of problem quite early. Because unlike a software company, where if you have to, if you found it, okay, we made a bigger, and we have to do a software patch, bar you've made some terrible architectural, decision that means you can't scale up your product and the product won't scale. Generally, you can fix a lot of problems by just releasing a software patch. The same isn't true in hardware. If you find you've got a problem like that, perhaps there's nothing that so an EMC engineer or signal integrity engineer can do to help you. Now, it's possible that you can, and perhaps you could shield the whole product. But if you have a Bluetooth product or a Wi-Fi product with a plastic enclosure, then of course you can't put a metal shield over everything. So you're not able to just enclose it and forget about it. You might have to go
right.
back, do the PCB.
Right. Some of the stuff you actually want to be emitting from the product is just in a very controlled way, hopefully.
Yeah, of course. But then you've got this garbage, that's being emitted as well, and you're failing your compliance testing, CE marking in Europe or FCC in the US, or whatever, and then you're really well-meaning. External test house tells you, look, guys, we can't sign this off, and often the test houses are extremely helpful. I know you've had guests in the past that talk about this, but they can be very helpful. Like, and there's some things like, okay, you put down on key traces to connectors coming off the board. Maybe you don't think you'll have a problem, but you'll put down an unpopulated 10 puff capacitor to ground, or you'll have a 0 ohm resistor that can be replaced with a wee inductor or a ferrite bead or something if needs be. And if you put those hooks on the board, the test house quite often, they know what they're doing. They'll go, oh, look, you've got a problem radiating from this connector here, but I see that you've made our job easy. You've put in some 0 ohm resistors there. Well, we'll just take those off and put in a wee ferrite bead or some type of choke or something in there to help you out, and we'll get the job done. But you make their job much easier if you accommodate those kind of things on the boards. But sometimes if you have a signal running over a split, there's nothing that can be done, unfortunately. And if you're like, you find it kind of comes up, like with hardware Kickstarters and that, and the guy says, you're going to have to redo those PCBs, and they go, oh gosh, we don't have the capital to do that. This is our product, we're shipping it.
Of course, yeah.
and that comes up a lot, I say, dealing with different types of clients. But and it's really disheartening, like, and quite sad, like, because these people have, poured their heart and soul into this product, but they weren't aware that this was an issue, and that they would need to address. And then, of course, because it's quite late in the day, when it arises, it can be difficult to solve. And even if it can be solved, then it is quite often it's great for consultants. They ring up in a panic. Oh my God, we can't ship our products because we can't get our paperwork in order. We'll pretty much pay you whatever you want, but this has to work. And
Right, right, right.
okay, great, like, fantastic. I'll get my near field probes, and quite often you can help people out. Particularly, look. Okay, you have to make those slits smaller, like, and there might be a trade off in thermal performance, but perhaps you need to make the slits a little bit smaller, like, so that a given wavelength doesn't find its way easily through a slit in an enclosure, something like that. And that can be easily done. Copper tape, or you 3D print. Well, maybe perhaps by the time you get to production, you wouldn't be 3D printing, but there's things that can be done. Whereas unfortunately in some products there can't be. You have to redo a spin. And so if you are a startup, you don't need to understand all or even anything that I've been speaking about in the last couple of minutes, but just remember, allow yourself some budget to do a respin, factor it into your schedule and your costs, and then bear in mind that this is, put it on your project plan. We need to do, compliance testing or regulatory testing, call it what you want. You mightn't understand what needs to be done, but there's plenty of people that can help you. But if you don't put it on your project plan, you'll just forget about it, and you might find yourself coming unstuck,
Yeah.
Unfairly, or, well, not unfairly, but of course, unfortunately.
So back to the integrity side of things, though, you're saying a lot of the things you might see are just jumping split planes and stuff like
Yeah,
that.
like, or
Other common issues you might see.
termination resistors in the wrong place, actually. Like, and this is a mistake. I mean, I've made all these mistakes. Like, I mean, I could write a book on the mistakes I've made, both from a business perspective, because everybody learns, when you be a consultant, but from a technical perspective as well. But signals running over splits, termination resistors in the wrong place. That's quite a common one as well. Because like I said, when I was in Xilinx, or in ADI, in the video DACs and video ADCs, a video DAC or ADC, or a HDMI transceiver, the RGB lines, there could be 36 bits wide coming out of an RGB ADC, plus the clocks and the sync signals. So RGB, each of them 12 bits, and it could be 36-bit bus plus clock and the syncs. And if you don't get the termination resistors in the right place, then you can have a whole bunch of energy bouncing around that board, as it tries to dissipate. It runs down, it runs down an unterminated line, and it comes back, and it just keeps on reflecting until that energy is dissipated. And that can be, like, and if that's on your clock signal, that's quite problematic. Like, I mean, and perhaps a way to describe it, like, on a podcast might be a clock is supposed to go tick tock, whereas if you have an unterminated line, you might end up with tick tick tock, and it's it's really not what you're looking for, because if that happens, then you're sampling at the wrong time. Aside from the EMC issues that you will cause, is that energy needs to dissipate somewhere, and you'll say, okay, when it's a series termination resistor, perhaps think of it as a source termination resistor, so that you put it at the source of the signal, and end termination resistor goes at the end of the line. And in in some products like FPGAs, or large DSPs, or even large processors, those termination resistors can be effectively incorporated into the design with active termination. But you do see that quite a bit, that people will just put down the termination resistor in the wrong place, and that's something that's quite unfortunate as well, because it can't be changed. It can't be changed post post layout.
Right.
Lesser problems can be like, actually sometimes another very common one is you have a first order RC filter, or maybe even a second order LC filter on a line. I know that I could either radiate noise out over a cable into the environment, so I should probably just bandwidth limit the energy that can come out off that cable. So you'll put down you'll put down maybe a very small, couple of picofarad capacitor to ground, and maybe a 1 to 10 ohm resistor in series, so you get a nice little RC filter. But then you find sometimes, I've had a couple of clients actually where they were a bit too aggressive with the value of the RC filter, and sometimes they confuse the termination resistor. They saw in a schematic somewhere, oh, it should have a termination resistor. Well, that should be 27 ohms or 33 ohms for some reason. I don't know why, but that's what we should put down. So they'll put down the 33 ohms, and they'll put down a fairly large capacitor, and then they just don't get the bandwidth that they need. The genuine bandwidth that they need for that
Oh
signal.
yeah, right.
And I had it one time even so
Yeah.
bad, like where
Some kind of thing is rolling off after
yeah,
some
yeah.
kind of corner frequency.
Yeah, like I had a guy one time. He said, "Oh, my audio product doesn't work," and it's kind of dovetailed nicely with my my various backgrounds, bringing in the signal integrity and the audio stuff, and it works fine at 1K, but at 10K, it's just doing nothing. And so, I think I might know what's going on here, and I mean, it's I mean, the issue was presented as a frequency response issue, like oh look, I need it flat from 20 hertz to 20K. I'm doing a really, it's really important that I get the full audio bandwidth, and at 10K, I'm just, it's terrible. I say, yeah, I don't even need to see the frequency response. I have a pretty good idea what's going on here. But but they're
Right.
they're much less problematic because if you put down a resistance to ground. If they put down a resistance to ground, a capacitance to ground, and it's not populated, but it's there, or they put a series 0 ohm resistor, that can be really useful because it helps, if you have noise on the board, you have an RC filter, if you have some kind of radiated emissions issue, like all these things. If you make things easy for yourself in the design phase, at the schematic entry point, anything coming off the board, try to allow yourself options, and then you don't need to be, people often describe all this stuff, it's black magic and everything, like, I mean, and it's a dark art, and like, quite often it isn't. It's just the laws of physics don't change, and all that comes into play is the parameters of your design, where they fit into uh, into the universe, like, really, and what you need to do to make sure that everything works nicely, like, so
Yeah.
yeah, I mean, yeah, really, the current flowing in loops, and again, that's the same with the splits, the signal crossing over the splits, that is the same problem, like, the outbound signal crosses over the split, but where's the return signal going? With a high speed signal, it tends to have, it's just a natural phenomenon, where it will attempt to the return path will attempt to follow as closely as possible the outbound path. And if your return, if the outbound path crosses over split, of course the return path can't do that, and that causes problems.
And when you say splits, you were talking about the power planes, or you were talking
Yeah.
about the ground planes as well?
It could be either. Actually, it's one thing that maybe people don't think of so much too. That a power plane can serve as a return path just as easily as a ground plane. People often think, oh, my return path for high speed signal will have to be the ground plane, but and for a low speed signal that may well be the case, but for a high speed signal, the return path, if there's, assuming that there's a plane there, will be the adjacent plane. So if you take a 4-layer stack up, typical 4-layer stack up in a PCB, it will be layer 1 will be a signal, layer 2 will be ground, layer 3 will be your power planes, and layer 4 will be signals again. Now, of course, there's variations and everything, but typically signal, ground, power, signal. And a high-speed signal on layer 4 will have its return signal or return path on layer 3. Now, if layer 3 is just made up of patches of power planes, then that can be completely appropriate and completely fine and completely resolve absolutely fine with the laws of physics, provided perhaps that the power planes are sufficiently decoupled. But if you think about it, I mean, in the past, people have, oh, how can that be the case? And there's obviously, good physical reasons why that's the case. But if you like to think about it, and it's perhaps not entirely accurate, but it does kind of get the point across that if you differentiate a constant, you get zero. So if you differentiate 5 volts and it's a constant perfect 5 volts, then it's zero, and zero sounds a lot like 0 volts. So that's very
Right,
very
right.
brief summary. How you can perhaps describe it kind of orally, in one sentence, and it's perfectly valid for the return signal to be on layer 3. In fact, that's where you want it. Again, you want to keep the loop as small as possible. So if the signal is on layer 4, you want the return path to be on layer 3 for a high speed signal. If you chop up layer 3 into lots of different islands of copper, because they're different power planes, 5 volts, 3.3 volts, 1.8 volts, then unfortunately the return path can't stay adjacent on layer 3 to the signal on layer 4, and then it will attempt to find a way elsewhere on the board, to complete the path. And then you start increasing the loop size, and you increase the overall loop area, and that has a whole bunch of bad side effects. So again, it comes back to the light bulb. You've got a light bulb, you've got an outbound signal, and you've got a return signal. Where is that signal going? And earlier when I said either you or James Clerk Maxwell are going to choose the return path, then you get down to the laws of physics and Maxwell's equations and everything, which will determine where that return path is. But you kind of you want to take it out of his hands and put it into your own hands as best you can, within reason.
Yeah, that's great. Well, I think that's probably a good place for us to wrap up here too. I think I saw on your Twitter that you said you have a Maxwell statue in your hometown now?
Oh yeah, oh yeah.
Something about Maxwell?
Oh, I'm a big Maxwell fan. So James Clerk Maxwell was Scottish, and he was born in Edinburgh. So the James Clerk Maxwell Foundation is here in Edinburgh on India Street. I think it's 14 India Street, and you can go and visit his house where Maxwell's born. So if you're ever in Edinburgh, you contact the James Clerk Maxwell Foundation. They have a museum set up to his life and works, and they have some really great exhibits there. And and you just have to, they're really passionate, enthusiastic guys, and you see some really interesting things there, and there's a plaque on the wall, and the IEEE have made a statue on George Street here in Edinburgh with Maxwell and his dog, and you see Maxwell's equations. Maybe on my Twitter feed, if you look back, you'll see Maxwell's equations on the ground in George Street. And a couple of years, I mean, it's been there less than 10 years. It's been there since I've moved to Edinburgh, but it was quite depressing at the start. I mean, he's quite often, considered the greatest scientist between Newton and Einstein, but very few people in Scotland knew who he was. And that's partially down to the nature of his work is maybe quite abstract for a lot of people.
Hard to grasp.
Yeah, right. And but this summer there happens to be an Italian restaurant just near the statue, and I was standing outside the restaurant waiting for waiting to meet somebody. And in the 10 minutes that I was standing there, I saw two fathers at different times. So I saw two fathers with two daughters actually, and both of them were coming along. They were tourists, and they were fathers explaining to their young daughters who this guy was, and the daughters were getting their pictures taken, with this guy Maxwell, which was amazing. It was
heck yeah,
it was great. I mean, it was even 10 years ago. I mean, I couldn't imagine it, but now I told my wife, like I was there, but like it was great. Like it was they weren't sons. I mean, they were daughters. Like the women in tech thing and is very important and growing, and it was quite pleasing to see actually. So he's he's so I mean the statue's there. You can get your on George Street, just near St Andrew Square, and like I say, on India Street you can go and visit basically a museum to him as well. And a lot of stuff happens here in Edinburgh. But actually, one last point on that is where Maxwell was born is just around the corner from where Alexander Graham Bell was born, and it's
really?
And it's just around the corner from where Peter Higgs lives. The Higgs boson. So like if you do happen to be in Edinburgh, just go down there and just start drinking the water and breathing the air. Like just do everything. So I mean, a lot of this comes back to the Scottish Enlightenment. 150 years ago, 200 years ago, Edinburgh was a real centre of learning, from Western philosophy and economics and science, and Lord Kelvin, was over in Glasgow, an hour away, and the Heriot Watt University in Edinburgh is named after James Watt. Is also a Scottish guy. So yeah, there's really a lot going on. And actually Dolly the sheep was was cloned or created or invented or whatever, in Scotland, So
Yeah.
there's a lot of good stuff here, and there's an awful lot of mixed signal electronics as it happens as well, So good little tech scene here. But it's only a city of
That's great.
half a million people, but a lot going on here. But yeah, I'm quite a big Maxwell fan, which that ties in nicely with my work and does go back to when I said at the beginning, kind of wrapping things up nicely is my final year project where I felt like such a fool, where the robot took on a mind of its own. And I said, okay, I'm going to get I'm going to get onto the bottom of this,
Yeah. So if people are stopping through at Edinburgh, where can they? How can they contact you, and where can people find you online?
Well, okay, so on Twitter you can find me at O'Leary Kieran, so Oleaory Kieran, Kieran, and or the company account is Mixed Signal Sys, so Mixed Signal Sys, also on Twitter, or the website is www.mixedsignalsystems.com, and there's a contact us form there. So yeah, absolutely, by all means, if you're in Edinburgh and you want to see the technical sites, you get literary walking tours and whiskey walking tours. There's no reason why you can't have a technology walking tour. There's enough here to do it. So it'd be great to catch up with somebody if they're in town. Yeah.
That's great.
Can I just do one really quick shout out, please? I won't keep you. It's just 2 seconds.
Sure.
Yeah, so I think we spoke, in 2015. So I was the general chair of a technical conference, EMC Compo 2015, and it's the full name of it was, the 10th International Workshop on the EMC of Integrated Circuits. So generally, EMC is thought of as a system level thing, and absolutely it is. But nowadays, there's more and more of a focus on EMC at the IC level, because there's more and more integration. You need to address some of these issues at an IC level, rather than at a system level, just because so much more of the system is on chip. And coming up later in the year, the 12th International Workshop on the EMC of Integrated Circuits is taking place in China. I can't remember the exact details, but it's in Shanghai or just outside Shanghai in September or October. And if you go to www.emccompo.org, I'm sure that the details will be there. And it moves around the world. Like, it was in Edinburgh in 2015 because it was the 150th anniversary of the publication of what essentially was Maxwell's equations. But it moves around the world, and it'll be in China. So anybody in Asia who wants to pop along, I'm sure those guys would be very happy to see you. And you can learn a lot about EMC and everything.
Looks like it's coming up in October. I just found it. It's October 21st to 23rd in Hangzhou,
I have it there.
China.
Yeah, in Hangzhou, Hainan is just outside Shanghai. But I mean, typically the guys that attend this would be, aerospace companies, automotive companies, because typically the guys, aerospace companies, like aircraft companies, Boeing, Airbus, all these guys, the automotive companies, the military companies, because they want to, they want absolute EMC performance. And in the consumer space, you can get away with a lot and deal with it at a system level, but these guys, with more and more integration, addressing more and more of these issues at an IC level is very important. And I know how much work was involved in doing the conference in 2015, and it was very rewarding, but it takes a lot of work, and it'd be nice to help these guys out in China. And if you can solve your EMC problem at the IC level before it even touches the system, or certainly approaches anywhere near your release date for a product, you'll be doing yourself a good favor. So if you happen to be in town or have the resources to travel to China, then I'd really recommend you go there if you can.
Awesome. Well, Kieran, thanks for being on the show and talking about all this stuff. I definitely look forward to talking more about this stuff and keeping my loop small so that Maxwell doesn't come and bite me.
Yeah. Oh, absolutely. Yeah. Well, yeah. Thanks for the amp hour. I mean, it's fantastic. It's really good. You just learn so much. Like, you can only learn so much in university or whatever, but really you have to see what people are doing and what they're up to and what real life problems they encounter, and it's fantastic.
Yeah. Well, thanks, man.
Yeah.
All right. We'll talk soon.
Okay. I'm off to bed now. Okay. Thanks, Chris.